Okay, so this is lesson 6-7 part A, and it's about Pascal's triangle. So we'll get to Pascal's triangle in a second, but what Pascal's triangle is useful for is helping to expand binomials. So this is a binomial, and it's called a binomial because you have two terms, and we're going to expand it by a certain number of powers. So in the first case, a plus b to the 0 is equal to 1, because anything raised to the 0 is equal to 1. What about a plus b to the 1? Well, that's pretty easy also. That's just a plus b. So now we have two things. A plus b to the 0 is 1, and then the next one is a plus b. What about a plus b to the second power? Well, that's the same thing as a plus b times a plus b, which is equal to, if you FOIL this out, you get a squared plus ab plus ab plus b squared. And then these two middle terms can add together, and so you get a squared plus 2ab plus b squared. So that's what a plus b to the second power is equal to. What about the third power? Well, that's a plus b times a plus b times a plus b. Well, we've already done a plus b times a plus b. We've done it once. It was a squared plus 2ab plus b squared. Okay, so let's FOIL this out. If you multiply a times all three terms, you get a cubed plus 2a squared b plus ab squared. Okay, now let's multiply b times all three terms, and you get b times a squared is a squared times b times 2ab is plus 2ab squared, and then b times b squared is b cubed. Okay, so now we can combine a few like terms, and we get a cubed plus, combine these two and you get 3a squared b. Combine these two and you get 3ab squared. Alright, so that is a plus b cubed. So you might start to notice some patterns, but let's do a few more. A plus b to the fourth is the same thing as a plus b times a plus b to the third. And a plus b to the third we did on the last slide, and it was a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, so now let's FOIL this out and multiply a times every one of these terms, and you get a to the fourth plus 3a cubed times b plus 3a squared times b squared plus a times b cubed. That's multiplying a times every term here. Now let's multiply b times every term, and we will get a cubed b from these two terms, and then b times the next term gives you 3a squared b squared, and then b times the third term gives you 3ab cubed, and then b times the last term gives you b to the fourth. Now we're going to combine like terms. That's all the stuff in the middle except for the first and last term, and you get a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Alright, so hopefully you're starting to see some patterns, but let's do it one more time. A plus b to the fifth is a plus b times a plus b to the fourth, and a plus b to the fourth was a to the fourth plus 4. Let me write the coefficients. I had 1, 4, 6, 4. Okay, so 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Okay, now let's multiply a times all of these terms again, and you get a times a to the fourth is a to the fifth. A times 4a cubed b is 4a to the fourth b plus 6a cubed b squared plus 4a squared b cubed plus a b to the fourth. Whew, that was a lot of writing. My hand hurts now. B times all of these terms, and you get a to the fourth b plus 4a cubed b squared plus 6a squared b cubed plus 4ab to the fourth plus b to the fifth. Okay, now again, the first and the last terms don't change, but everything else you add together, and we get 5a to the fourth b plus 10a to the third b squared plus 10a squared b cubed plus 5ab to the fourth plus b to the fifth. Okay, so why are we doing all of this binomial expansion? Well, let's write it all together on one slide. So we found that a plus b to the 0 is equal to 1. A plus b to the 1 is a plus b. A plus b squared is a squared plus 2ab plus b squared. Here's a plus b cubed, a plus b to the fourth, and a plus b to the fifth. So go ahead and pause the video now and see if you can find some patterns, and then I'll point out a few. Okay, so here are some of the patterns. You may notice that you have b squared, b cubed, b to the fourth, b to the fifth on the outside. Over here you have a squared, a cubed, a to the fourth, a to the fifth on the outside. And if you think about 1 as a to the 0, or b to the 0, then you have b to the 0, b to the 1, b to the 2, 3, 4, 5, and it just keeps going on the outside. And that makes sense because we saw when we were multiplying, you always had that outside term that was being added in the end. Okay, so here's a couple of other patterns. If you look at each individual line, you start with, let's look at this last one because it's easiest to see, a to the fifth, then a to the fourth, a to the third, a squared, a to the first, a to the 0. So a starts with 5 and counts down to 0 when you have a plus b to the fifth. When you have a plus b to the fourth, a starts with 4 and counts down to 0. B does the opposite. It starts with b to the 0 and it counts up to 5. So b to the 0, b to the 1, b to the second, b to the third, b to the fourth, b to the fifth. Now obviously you don't need to write b to the 0 or a to the 0 because that's 1. So that's a really important pattern. Here, a squared, a to the first, a to the 0. So if I said a plus b to the 10th, I know it would start like this, a to the 10th, and then it would go a to the 9th, a to the 8th, a to the 7, all the way down to a to the 0, and then the b's would go the other way. This would be b to the 0, b to the 1, b squared, b cubed, and then this would be b to the 9th, and this would be b to the 10th. It just counts down. If you notice, if you add up the two exponents, 10 plus 0 is 10, 9 plus 1 is 10, 8 plus 2 is 10, 7 plus 3 is 10, 9 plus 1 is 10. Okay, so if you add up the two exponents in any term, 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4 is 5. So that's a very important pattern. Now I would be done here if I could say something about the coefficients. If I knew what was the number that went here. Well, you actually can because there are some patterns in the coefficients also. This is 1, this is a 1, and this is a 1. 1, 2, 1. Now if you notice 1, 3, 3, 1. If you remember where this 3 came from, it came from adding a couple of the middle terms together. And actually, if you look at the coefficients, if you add 1 plus 1, you get 2. If you add 1 plus 2, you get 3. If you add 2 plus 1, you get 3. And that pattern continues the entire way. 1 plus 3 gives you 4. 3 plus 3 gives you 6. 3 plus 1 gives you 4. 4 plus 1 gives you 5. 6 plus 4 gives you 10. And that pattern continues. This pattern is what creates Pascal's triangle. So if you start with a 1 and then you add these two 1s here, if you imagine zeros going on forever on either side, 0 plus 1 is 1, right? 1 plus 0 is 1. And then you have 1 on the outside, 1 plus 1 is 2, and then put a 1 on the outside. So all these outside ones are going to be 1, okay? So you can go ahead and write those. And then 1 plus 2 is 3. 2 plus 1 is 3. Okay, this is a plus b to the 0. This is a plus b to the 1, 2, 3, 4, 5, 6. Now something else you might notice, another pattern is, the first number that's different than 1 is also the exponent, 3. So this one's 4, this one's going to be 5, this one's going to be 6, 7, 8, 9, 10, 11. I could keep that pattern and I could just keep writing, filling in Pascal's triangle this way. Okay, then if I fill in the middle, 6, 4 plus 6 is 10, 6 plus 4 is 10. Okay, I'm going to fill this in really fast now. Okay, so this is real time. I can just write and think really quickly. So I'm going to do this up until about 10 rows, and then I'm going to stop. So if I was going to use Pascal's triangle to expand a plus b to the 8th, I would look at the row that has the 8 as the first number, because that's going to be a plus b to the 8th, and I'm going to use these coefficients, and I'm going to write a to the 8th, because that's where I'll start, plus the next coefficient is going to be 8, a to the 7th, b, plus the next coefficient is 28, a to the 6th, b squared, plus the next coefficient is 56, a to the 5th, b cubed. The next coefficient is 70, a to the 4th, b to the 4th. And once you get to the middle, the coefficients start repeating. 56, a cubed, b to the 5th, plus 28, a squared, b to the 6th, plus 8, a, b to the 7, plus b to the 8. 1, b to the 8th. And this is the expansion of a plus b to the 8th. That took me a lot less time than if I had done it foiling out each of those binomials. Okay, then we can also solve problems like this, x minus 2 to the 3. If we solve this first, a plus b to the 3, we know that's going to be a cubed plus 3a squared b plus 3ab squared plus b cubed. And then if we substitute, a is equal to x and b is equal to negative 2, we can substitute in for a, x, and b, negative 2, and then we can simplify this. This is going to be x cubed plus 3 times negative 2 is going to be negative 6, so I can say minus 6x squared. Negative 2 squared is 4, 4 times 3 is 12, so plus 12x, and then negative 2 cubed is going to be negative 8. So here is the binomial expansion of x minus 2 cubed. And one more, x minus 2 to the 5th. Well, we have a plus b to the 5th is equal to a to the 5th plus 5, a to the 4th b, plus 10, a to the 3rd b squared, plus 10, a squared b cubed, plus 5, ab to the 4th plus b to the 5th. And then we substitute a is equal to x and b is equal to negative 2 for each of these terms, and we get this. When you substitute in all of those values, this is what you get. And then when you simplify it term by term, the first term is x to the 5th. The second term is negative 2 times 5, so that's going to be negative 10x to the 4th. The next term is going to be 4 times 10, which is 40 x cubed. And if you expand the entire thing, you get this as your final answer. So the next lesson we're going to talk about the binomial theorem and another way that you can expand things quickly. But that's it for the Pascal's triangle.